Hello everyone. Today is a short video on 9i, which is the derivative of circular functions. You just need to look back at chapter 6 on circular functions before you move on to this, or you just can refer to it at the same time. With the three main trigonometric functions, which is sine, cos, and tangent, they are defined as the derivative of sine is going to be cos, the derivative of cos is going to be negative sine, and the derivative of tangent is what we're going to call, it's a function called sec to the power of 2. Now if we apply a chain rule, which is a composite function of starting from kx to the circular function, which is either sine, cos, or tangent, what you end up with is, with the first derivative, is having a coefficient k that comes out for the first derivative. So the derivative of sine is going to be k times cos k of x, which is your first function. Do the same with cos, we do the same with tangent. Now the sec function, if you haven't done specialist, is what we call the reciprocal function of cos, and that's the secant function. One of its abbreviation is sec, okay, and it means 1 over cos of theta. Just be mindful with that. It's that function cos can become 0, so when you define the domain of sec of theta, you will need to exclude certain values like pound 2 plus 2k pi, or k pi, because it's also negative pound 2. Let's look at a few examples. The first example, if you were to apply just the rule from the previous slide, it will be 4 times cos of 4x, but let's break it down using the chain rule. So using the Leibniz notation, we call u 4 of x, and the sine function is going to be y equals sine of u. You differentiate respectively both of them in terms of the variable. So du over dx is 4, and dy over du is going to be cos of u. We, after dy over dx, using the chain rule, is dy over du times du over dx. We replace by what we just calculated above. That's 4 times cos of u. You replace u by the original function, which is 4x. Next one, we have negative 3. So negative 3 is a constant factor, so we keep that on the side when we differentiate, and you need to keep it for the derivative, but you don't need to change anything. Here we're going to apply a chain rule. So u is 2x minus 5, y is negative 3 sine of u, so that negative 3 will not change. We differentiate 2x minus 5, the first derivative will become 2, and dy over du is going to be negative 3 cos of u. Using a chain rule, it's the product of dy du by du over dx. That gives you negative 3 cos of u times 2. We simplify and resubstitute u by its expression in terms of x, and we get negative 6 times cos of 2x minus 5. Last example, so you need to differentiate, but here you need to find, first you need to find the y coordinate. So that's just substituting the x coordinate into your function, the gradient of the tangent. So to determine the gradient, first you need to differentiate, find the first derivative, and then you need to substitute the x coordinate to obtain a value for the gradient. So let's look at the function, which is in terms of theta. So just be mindful, the notation may vary, but mentally think that's my x, okay? So y equals sine of theta, that's the y coordinate. The gradient is going to be dy over d theta, and we'll substitute those two values. Y equals sine of theta, dy over theta is cos of theta. Okay, so for the first point, the on the x-axis is theta equals pi on 4. We get y equals sine of pi on 4 using your exact values. It's 1 over root 2 or root 2 on 2 if it's rationalized, and dy over dt d theta is cos of pi on 4, which is root 2 on 2. So the coordinates of the point are going to be pi on 4, 1 over root 2, and the gradient is going to be 1 over root 2. So just be the same value, but it being obtained differently. For theta equal pi on 2, y equals sine of pi on 2, which is 1, and dy over d theta is cos of pi on 2, which is 0. So at the point pi on 2 equals 1, the gradient is 0, which is a horizontal tangent, and it could be potentially a turning point. Okay, and that's it for this session on 9i. See ya.